starts this way. The AP Chemistry exam is 3 hours and 5 minutes in length. It consists of a multiple choice section and a free response section. The 90-minute multiple choice section contains 75 questions, just like the sample does, 50% of the final grade. The 95-minute free response has 6 questions, that's 50% of the grade. Part A is timed, and that is 55 minutes for just Part A. Part B is 40 minutes long. A 10-minute break will be given after Section 1 is completed, and Section 1 being and then that would be your multiple choice. And then students will be given a 10-minute warning prior to the end of parts A and B in Section 2 of the exam, the open-ended or free response. Everything is administered in one session, one 3 hour and 5 minute session. Students will have the most realistic experience if a complete morning or afternoon is available to administer. All of those things you will have done. Many students wonder whether or not to guess the answers to the multiple choice questions about which they are not certain. It is improbable that mere guessing will improve a score. However, if a student has some knowledge of a question and is able to eliminate one or more answer choices as wrong, it may be in the student's advantage to answer the question. Now, I don't know if they did this, I think this is true of the SAT too, where you no longer are penalized for guessing.
I think that's
Well,
I was
they said it starts next year for SATs.
Okay,
AP
so if it starts
this year.
next year, then I believe, because we got a message on it, and I couldn't remember if that was this year or next year.
Mr.
It just says it may be your advantage
was
to
saying it was
answer
this
each
year.
question. What's
Wallace was saying that it was this year that they stopped penalizing for guessing.
I think it might be on AP Pass.
Okay, because I knew I got an email on it, and I thought we said it was for next year for SATs. I thought for us we got it for this year. So yeah, you will not be penalized the extra quarter of a point that you were before. And some people, when we used to be penalized for guessing, would say, well, if I just don't answer them, I can get 100%. You can't. You can't get 100% if you don't answer all of the questions. You just don't miss as many points. Well, now you're not penalized for guessing, so it's probably best to answer each. The use of a calculator is permitted only in Section 2, Part A. Here. That's it. No question on the multiple choice at all.
Are there going to be questions on the multiple choice that will require calculation?
All of the calculations should be able to be done without a calculator. Now here are some of the more difficult ones, and you'll see them on there, logarithms. And here's why you should be still able to do them. The log, let's say the log of 1 times 10 to the negative 6. You should know that that is 6. The log of 1 times 10 to the negative 5th is 5. So then if they gave you 5 times 10 to the negative 5th, you should be able to have an estimate as to where that is. They're not asking for you to do these enormous calculations, but they're reasonable calculations. And you can see that if you look through some of the sample multiple choice questions. So the calculator is permitted only in Part A of Section 2. After time is called for Part A, students will have to place their calculators under their desk. The use of electronic devices such as a cell phone will not be permitted in any portion of the exam. It is suggested that Section 1 of the practice exam be completed using a pencil to simulate the actual administration. Students can use either pencil or pen for Section 2, that is the open-ended. They will provide you paper to answer your free response questions. Teachers should provide directions to the students indicating how they wish the responses to be labeled, so the teacher will be able to associate the student responses with the question the student intended to answer. Periodic table of elements will be given, that is the sheet we've been using all year. Remember that students are not to remove any materials, including scratchwork from the testing site. Students cannot have QWERTY keyboards or be designed to communicate for keyboards or be designed to communicate with other calculators such as infrared ports. So that's essentially the rules at the beginning.
For the periodic table sheet you're giving us, is it going to be the same as ours with all of the equations on there as well?
Yep.
Okay.
The one you've been using all year, I took from last year's exam. That way
Okay.
you should have no questions as to what's on it. It should be exactly the same.
Okay.
Okay, so I gave you some study material, some things like that you should know. And there's a lot there. But you'll notice most of it is just kind of just some reviews materials. On this one, it talks about ligands, what a ligand is, and this is with your complex ions. The ligands being the Lewis base, as we talked about today. The central atom is a Lewis acid, and then the reactions with those, and they've been those complex ion reactions you've been doing all year. They have an example of the organic section, just a small portion of it. I would say, if I were giving any advice, know what you know well. So that means if, let's say, you didn't have a chance to get to the organic, not that it's a good thing that you don't know it going into the exam, but you can do very, very well with just some minor deficiencies here. What you know well. Don't go in with trying to know a huge amount of material, but only know a little bit of all of it. What you know, if you know it really well, then you should be in good shape. We didn't talk about nuclear reactions this year. I'm assuming that you know a lot of that. So there are some things on nuclear reactions here. Delta S, solubility, which we're going to talk about. There are bond orders, electrochemical cells, hybridizations, quantum numbers. The way this chart reads is the intermolecular forces. The greater, and that's why it's more bolded, the greater the force, the greater the boiling point, and so forth. That's why those are bolded and larger. And then on the back, here there are activities of metals. Here are your kinetics. On the back, your ions you should know, solubility rules, oxidizers, again, they're ones we've been using all year, and reducers, gases, electrolytes, driving forces, all of those things which you've already done. Now, this quick review is really not that quick because there's 15 pages, but it does offer you a lot more detail than the first one does, where this one goes into a little more as to what you need to know about atomic theory. And it gives you some actual notes on it. What you need to know about, in this case, periodic trends. What you need to know about hybridizations, geometries. And this one looks like sigma and pi bonding, polar and non-polar. So this is a lot more comprehensive, and this just complements that. It gives you a little bit more of the same thing, but it they go hand in hand. So if I were to tell you to look at anything, these two would be a good place to start. Also with that, the booklet you got with your, you got a booklet with your book. There was a preparing for the AP exam. I believe they have practice exams at the end. It's another way. The blue books that we have practice exams in them. And then I'm going to give you the take-home final, 11 questions that you can do. And then with these study sessions, I want to look at these things. And I'm going to start at the nearest exam, which is last year, 2010, and then I want to work through some of these things so that hopefully you can see from the 2010 exam how you should have answered the questions, and then from that, maybe you'll feel a little comfortable with doing the questions on the test itself in about a month. So the first one I wanted to look at was question 1 on 2010. Again, those blue books, if you haven't got one, feel free to take one. There are, I believe, some very good sample multiple choice as well as in your book. In that gray book, I believe there are a lot in there too.
Which one's the actual test?
The one that says AP Chemistry Free Response Questions 2010. Okay, I want to start with that one. And when you look at this, it says several reactions are carried out using silver bromide, which is a cream color, silver salt, for which the value of the solubility product, KSP, is given. Write the expression for the solubility product constant. Now, this is where I think you would maybe be a little concerned at this point, because you say, we haven't done KSP. So how in the world are we supposed to do that if we've never worked with KSP? Well, I wanted to show you that it's actually not that difficult. This reaction is for silver bromide, which is a precipitate. So it's a solid. Now, one of the misnomers that we bring up in honors is that things are insoluble. Silver bromide is just for the most part insoluble. It isn't beyond reason to believe that silver bromide actually breaks down to silver ions and bromide ions. To the extent that since this is for solubility, we did Kc. That is for the equilibrium of gases. Kp is for their pressures. Ka is for the equilibrium with aqueous weak acids. Kb for weak bases. Well, now when I'm looking at a solid that breaks down, we call this its Ksp. And in this case, they give me Ksp as 5.0 times 10 to the negative 13. Now what that means is there is very little of this product, which makes sense because we would have said this was insoluble. Now when you write the K expression, normally it's what over what?
Products of a reactant.
Products over reactants. What's true of the reactant then?
It's a solid.
It's a solid. It doesn't show up. So then the Ksp is equal to the concentration of Ag plus times Br minus. And that's it. The same as what we did with gaseous equilibrium. Solids aren't shown. If I had a coefficient here that would go in front of the Ag, it would still be used as a power that was raised to. In this case, there is none, so it stays as is.
So Ksp is just for insoluble.
Yeah, because the Kc is the K for gases. The Ka and Kb is the K for acids and bases. The Ksp is now the K for things that are solid.
Okay, so everything that's soluble then is covered under Ka and Kb.
If it's a soluble salt, now the K would be really, really big, so it's actually not even used.
Okay.
When we do Ka and Kb, that's actually for things that are aqueous, that don't break down completely. So if Ka and Kb cover acids and bases only, those things that are aqueous in solution. These are not aqueous, so that's why we use their solubility product, not their Ka or Kb.
Okay.
That's it. Part B then says, and the scoring for this would be 1 point if you got this correct. And notice the parentheses indicating their concentrations. It says you have 50 milliliters. What's the concentration of Ag in 50 milliliters of a solution of AgBr? Okay. Well, normally what we would do is we'd set up an ice chart, right? So if I tried to set up an ice chart, I want to show you why I'm not going to set up an ice chart. AgBr would go to Ag plus Br minus. Here would be my ice chart. That's a solid. So its concentration stays relatively constant. These would be initially 0, right?
Right.
Then it would be plus x, x and x. So I don't need an ice chart to know that these are both going to be x. So that Ksp will be equal to x times x. Now what is x? X is the amount of Ag and Br in solution. It's how much Ag I gained, it's how much AgBr I lost. That x is its solubility. So that this x will always equal the solubility of the salt. So I knew the Ksp was 5 times 10 to the negative 13. It's equal to x squared. I square rooted both sides, and when I did so, I got 7.1 times 10 to the negative 7. And that's it. That's all they wanted to know was, what is the value of the silver ion concentration? X. It's also the bromide. It's also what we call the solubility. It's how much of the silver bromide I lost.
So wait, did 50 come into play at all?
It actually is irrelevant.
Okay.
It actually doesn't matter. Which leads you into part C. Part C says a 50 milliliter sample of distilled water is added to the solution in B. So that's 50 milliliters, so now it's 100 milliliters. So a 50 milliliter sample is added to the solution in part B, which is in a beaker with some solid AgBr, which makes sense because it means that all of the silver bromide didn't break down, only some of it did. The solution is stirred and equilibrium is reestablished. Some of the solid AgBr remains on the bottom of the beaker. Is the silver ion concentration greater than, less than, or equal to the value you calculated in part B? Justify your answer. Let's think. I add water to this. Will it have any effect on the solubility? Again, it says you have 50 milliliters of water, and it's in the beaker with some of the solid. Solution is stirred, equilibrium is reestablished, some of the solid AgBr remains. Is the concentration of silver greater than, less than, or equal to the value that you calculated in part B? It should be the same. The amount of the silver bromide that breaks down is not based on the volume you have. It's based on the temperature at which this is occurring. So it should stay the same.
So KSP is only affected by temperature, just like
Yeah,
KC?
just like all K values are temperature dependent.
Okay.
Like every K we do is essentially like the same calculation.
They're all done the same way. They're all products of reactants. They're all raised to the power of their coefficient. They're all, you ignore a solid or a liquid in all cases, yes. So that was part C. So again, the value of the silver ion should be equal to that in part B, because it depends on the concentration of ions, not the volume. Okay, then it says calculate the minimum volume of water in liters necessary to completely dissolve 5 grams of silver bromide. Okay? And they give you the molar mass, so that you didn't have to look that up. That's pretty nice of them. So I have B, 5 grams of AgBr.
Nice chart.
Well,
I write down sort of the things on.
let's go back to, I need to go back to this. This 5 times 10 to the negative 13. Let's see if I have it. So let's see. So they tell me I have 5 grams of silver bromide. Let me go back and read this one more time. So I have 5 grams of silver bromide. And I want, what is the molar mass? That's 188. And I want to completely dissolve all 5 grams.
Do you use them, find the moles of AgBr and
The first step I would do is to find the moles of AgBr.
KSP? KSP is molarity, right?
KSP in this case would be a molarity squared.
Wait a minute. Would this even matter? Because you said that the more water you add, you don't change.
Well, we're just saying you have 5 grams of this. We're not looking at this at all.
We're not looking
So
at
this
the
is
same
just, you have 5 grams of silver bromide. How much water do you need to add for it all to be completely dissolved?
Oh, okay.
Now, here's what we need to think of. When you put silver bromide in water, it dissolves to the extent that how many silver and bromide ions are there? Yeah, what's the molarity of silver and bromide ions in solution? And this we actually already calculated.
7.1 times.
7.1 times 10 to the negative 7. So if this were my initial concentration, then all of it will dissolve. See, we're assuming that you have a lot more than this. But if I have at least this concentration, then what happens is all of my silver bromide will be converted to silver and bromide ions. So
Okay.
this is the concentration of silver I'm looking for. The silver that's going to come from the silver bromide. So you were right to say convert this to moles. Gives me what, 188?
Yes.
So when you do that, 0.0266 moles of AgBr. Now we know that because of its KSP, that the molarity when the silver ions are in solution is going to be, what was it, 7.1
Times 10 to the negative 7.
times 10 to the negative 7. Now for every one silver bromide, there's one silver, so that's why I'm using the 1-to-1 ratio, so that this would be 0.0266 moles.
So you just cancel units to get liters.
And then this will give me liters. Molarity is moles over liters.
So could you technically do that in like a stoichiometry sort
Yep.
of fashion?
Definitely.
Almost
Oh yeah, because then you could get moles here, and then the 7.1 moles for every 1 liter. If you solve for x, then you get 3.7 times 10 to the 4th. Is that right?
Yeah.
That's a lot. So the idea is, and kind of from this you should see this. I don't think it would be, I think it's D. The idea from this is such a small mass of silver bromide requires a tremendous amount of water for it to become soluble. This will give you a concentration such that it is so small that it'll actually become soluble.
So it won't be like an idea where that would be a ridiculous number to see on the test.
No, not in this case, no. Because it makes sense, because silver bromide is so insoluble that if you wanted to dissolve it, you need a tremendous amount of water for a very, very, very small amount of solid. What that does is it says, okay, this is dissolving all the time. To what extent? To the extent that you have only 7.1 times 10 to the 7 moles per liter of ions. Well, if that's what I started with, then they will actually dissolve. Part E. Is there another one of these? A student mixes 10 milliliters of 1.5 times 10 to the negative 4th with 20 milliliters of 5 and stirs the mixture. What did the student observe? I don't know if you remember us doing this, but this all goes back to this portion. Reaction quotient Q, because you know this. Right? So what I'm going to do is I'm going to solve for Q. And if you're at equilibrium, these two should be equal. If you're not at equilibrium, the reaction will shift in one way or the other to reestablish equilibrium. So I'm actually going to solve for Q, using what they gave me. So I add 10 milliliters of 1.5 to 2 milliliters of 0.5. So I need to figure out what that concentration is of silver. So I'm actually going to look at that over here. So silver is 10 times 1.5 times 10 to the negative fourth is equal to, and I added 10 and 2, so it's x times 12. So I'm able to get the concentration of the silver ion that's added. And I need to do the same for the bromide. There's only 2 milliliters of this. 5.0 times 10 to the negative fourth. And it's still equal to x times 12. And when you solve for x, the bromide solution, you should get 8.3 times 10 to the negative fifth. These values go in for your concentration. So you would plug the x in this case. This is your silver ion that was added. This is your bromide ion.
How do you get 12?
Yeah.
The 10 that I added of silver, and I added it to 2 of the bromide. So the total volume of the solution is now 12 instead of 10.
That's M1 V1 equals M2 V2.
Yep, M1V1 equals M2V2. And I solve for Q to see how close I am to KSP. When I did that, I got 1.1 times 10 to the negative 8. Keep in mind from the previous page, KSP was
7.1 times 10 to the negative 7.
5.0 times 10 to the 13. So I add these two solutions together. How does Q relate to KSP?
It's larger.
It's, wouldn't you say it's much bigger? So what does that mean about the ion concentrations?
Too high.
They're too high. They have to go
Down.
down. Which way is the equilibrium then going to shift?
Towards the solid.
So then what did they say? What do you expect to see, right?
Precipitation.
What will you observe? Precipitation. Right? The reaction must shift in such a way as for Q to equal KSP. How is that going to happen? When the silver and bromide ion concentrations go down, which would make precipitate. Now, part F, it says the color of another salt, silver iodide, is yellow. So you have to, I guess I'll work over here. Remember before you had AgBr, solid, breaks down to Ag plus Br minus. KSP is 5.0 times 10 to the negative 13. And this was, I believe, a cream-colored solid. They tell you that another salt of silver, silver iodide, is yellow. Now, I don't believe they give me a KSP here. They say a student adds a solution of NaI to the test tube. Well, in our case, they're really adding what? Na or I? What's the most important part of the precipitation?
The Na?
Well, the Na is not going to react with anything that's here. See, by adding I, I'm actually adding a common ion to something that's already there, or I'm adding something that can react with either of the silvers. Na will react with bromide and iodide to become NaI, which doesn't react. But if I add I minus, it can react with silver to make silver iodide, or it can force this reaction and this reaction here to go back again to silver iodide. So it said NaI, student adds a solution of NaI test tube containing a small amount of cream-colored AgBr. Telling me that I minus was added to a test tube that AgBr. Now, if it has AgBr, don't forget, it also has trace amounts of silver, at least some small amounts of silver and bromide ions. What extent? 7.1 times 10 to the 7th molar. It says, after stirring the contents of the test tube, the student observes that the solution in the test tube changes from cream to yellow. So then they want to know, what is the reaction taking place? Well, what must be happening for it to go from cream to yellow?
Ag is reacting with I minus.
Okay, so the AgBr that was there must be reacting with the I minus in a way that you get AgI plus Br minus. That was Fi. Now the question is, which salt has a greater KSP value, AgBr or AgI? So what it looks like to me they want to know which one has the greater KSP. Now, the greater the KSP, the more ions you have in solution, right?
Yeah.
So here's what they mean by that. So I think, and I just have the first one to go by, right? Yeah. Yeah. From what I see, what does this tell me? Any guess as to which one is greater?
The AG, wait a minute, it would be the AgBr?
It's actually this one.
Is it because of the reactivities?
Well, it actually is. It's because, see, here's what's going to happen. This AgBr, the only reason it reacts is because you're getting the I minus to react with the Ag from here. The thing is that this AgI would also be breaking down. So that it is, from this, if this AgI broke down better, it could react with AgBr and go the opposite direction. So that what we're seeing is a predominance of the forward reaction. So since there's a predominance of the forward reaction, it must tell me that this KSP is much greater, since it actually seems to be reacting, meaning it's producing more silver ions. In the products, enough silver ions aren't being produced to react with the bromide to make the cream-colored solid. This AgBr produces more ions, therefore it can react with the iodide better than the iodide here. This silver could react with the bromide. I think that answers this question. A little tough because we haven't done this yet, but the good thing is we will do this before the AP exam. But I wanted to show you this not because I necessarily wanted to get into KSP, because we'll do this, but I wanted to show you that this is done the same way as KC and KA and KB and KB. There's just a little more of a thought that had to go into it than since we didn't know anything about this. Since we knew very little. Okay. Number 2 said a student performs an experiment to determine the molar enthalpy of a solution of urea. They give you the equation for urea. They say that they place 91.95 grams of water and 25 grams Celsius at 25 degrees Celsius in a coffee cup calorimeter and immerse a thermometer in the water. After 50 seconds, the student adds 5.13 grams of solid urea into the water and measures the temperature of the solution. A plot of the solution is shown. Determine the change in temperature from the results. So, from what I can see, what do you notice? What is that 25 degrees Celsius? Why is there a plateau there?
No.
It actually has nothing to do with that. What do you think happened at, because it said after 50 seconds, what happened after 50 seconds?
That's when he added it.
So yeah,
There was
that's
no
when the
reaction.
reaction starts. So what kind of reaction is it? It's endothermic, right? Why does it level out again?
Reaction ends.
That's where the reaction ends, right? So what was if they want the delta T, that must be the final minus initial temperatures? Well, delta T, yeah, it seems like it's more complicated than what it is. What was the final temperature?
21.
21.8 is what it looks like to me. Minus the initial, which was
25.
25. When you do the math, negative 3.2 degrees Celsius. So then they want to know, according to your data, is the dissolution of urea in water an endothermic or exothermic process?
Endothermic.
Endothermic, right? And we know that why. So we have a negative delta T. So, which would mean a decrease in temperature. So that the water, whatever the water is, the solution isn't, normally we see exothermic reaction, the temperature is going up. So the water is, you're seeing this tremendous amount of heat released to the water. Now we're seeing the water actually losing its heat. So that the water is actually losing its heat to the reaction, so the water is actually having its heat absorbed. So there's a decrease in temperature, and that should tell us that. So there's a loss of energy to the reaction, meaning it's absorbed. Okay, part C says assume the specific heat capacity of the calorimeter is negligible. So they're assuming that the cup doesn't absorb any energy, and that the solution has a 4.2 specific heat. Calculate the heat of dissolution of the urea. Okay, so you're going to use Q equals MC delta T, and they give me. Right. They want. I'm just looking at to see where they. Heat of dissolution of urea and joules. Okay. So when they set this up, you know there's MC delta T Now the mass, you have to be careful because it's the mass of this solution. So this solution has a full mass of 97.08. 4.2, and the temperature change was 3.2. You get 1.3 times 10 to the third.
Yeah.
So this comes out to negative 1.3 times 10 to the third. Now what we have to be careful of is the Q of the reaction is equal to the negative Q of the actual substance that is absorbing it. So we're looking at, this is the Q of
The water.
negative. So in order to find the Q of the reaction, we need to take the negative of this Q. Because negative Q of the reaction equals the Q of the solution process. So the negative Q of this would then be equal to 1.3 times 10 to the third joules, which makes sense because it should be an endothermic process. So we have that part. D. D says now calculate delta H of urea. So the delta H would be this 1.3 times 10 to the third. Was that what it was? 1.3 times 10 to the third? So I wrote it down. Well, then it's positive though, because it's an endothermic reaction. So then it's 1.3 times 10 to the third in terms of the reaction, joules. But that is for every, what was that, 5.25?
5.13.
Yeah, 5.13 grams of urea. If you add up urea, it's a pretty easy one. It's actually 60 grams is 1 mole. So when I did this math here, I got 1.5 times 10 to the fourth joules per mole. I can't remember, did they ask for it in kilojoules? Yeah, in kilojoules, well, then that must be 15 kilojoules per mole. That was not too bad. D. E. Oh, wait, that was, sorry, that was part 2 of C, so now it's on part D. It said, using the information in the table below, calculate the molar entropy of solution, so delta S, for the reaction. Okay. Well, why do they give me delta H and delta G? And delta G equals, well, delta H minus T delta S. And then the delta G they gave me is negative 6.9. Delta H they gave me is 14. Minus, and what's T?
298.
298, right?
Yeah.
And then delta S is X. And you solve for X. You get 70 joules per Kelvin mole. Okay, the student repeats this experiment and this time obtains a result for delta H of the solution that is 11% below the accepted value. Calculate the value that the student obtained in his second trial. So what we got? 11% below, what do you get to do there?
14 times 0.11.
Times 0.89.
Yeah, so the 11% of the accepted value is delta H. So what's the accepted value of delta H?
What?
I think you said it was
14.0.
14. So I took 11% of 14. Or you could have taken 89%, right, to get what they got, find out what they got. And I get 1.54 kilojoules. So that's how much they should have been off by.
So
So I took 14 minus 1.54, and I get 12.9. Okay, then it says the student performs a third trial, but this time adds urea that has been taken directly out of the refrigerator at 5 degrees Celsius. What effect, if any, would using cold urea instead of that at 25 have on the experimentally obtained delta H of the solution? Justify your answer.
it would increase it, right?
So let's see, where's our, we started normally at 25, right? So now we're starting at -5, is that right?
So
So,
2 smaller.
let's see. So now the urea is actually going to go from 5 to, let's see, we're still going,
You would go from 5 to something higher. Wouldn't it? So it would be lower than 23?
so it's still in, now, so I'm still going to, the delta H is still the same, right? We're still using the same urea, aren't we?
It's delta H of the solution.
Yeah, it's-
Okay.
Right, I mean, I'm saying we're still using, if I read this correctly, perform the trial, so you performs a third trial, this time adds urea, so I'm assuming it's the same amount, directly from the refrigerator at 5 degrees Celsius. So if I was doing this equation, he should still get this amount of Q, shouldn't he? Right?
Yeah.
Should still get the same heat that is evolved or heat absorbed.
Would he because the temperature's different?
Temperature's much lower.
But shouldn't the urea itself, dissolving it, the urea process, shouldn't it have the same delta H value? Right?
Okay. Okay,
So what I'm
thinking
saying is, if it has the
solution.
same delta H value, then this number should be the same. It should still lose the same amount of heat per whatever number of grams.
Okay.
So that 1.3 times 10 to the third joules are still lost for every, what was this?
5.13 grams.
Well, this is going to be the whole solution is 90.
91 point.
Well, then remember we had to go together.
97.08.
Okay, this was 4.2, and now we can solve for x. And we should find a temperature change that is actually higher than what we saw before.
Okay.
Let's see what do you get for a number?
3.19.
You got 3.2?
Do the same reaction again.
That's got to be the same. Let me go back. That still comes out to the same.
It's not the same reaction we did earlier though, just using.
Yeah, it's just
Yeah,
you
because
putting
it's
in the Q.
Yeah, exactly. I guess I used that. Should have.
Plugging in the answer we got.
Yeah, 'cause it's not going to give me that's right. It won't give me the same. So I'm solving the same thing back. That's not, doesn't make sense. Let me think. So let's see. We're doing it at a lower temperature, right?
Right.
Yeah.
So
That's
we're
the only
adding, let me
difference.
see. So adding 5 degrees Celsius instead of it was
25. degrees Celsius.
degrees Celsius, right? So let's see. So we know that this process, we look back at our graph. So see that it drops for 21. Okay, that makes sense. Then forms a third tropical. This time it adds urea that we're taking directly out of the refrigerator.
Well, the final temperature
No.
of the reaction might be the same.
I'm trying to think if
Delta H would still remain the same.
well, see, the delta H wouldn't be the same because the delta H 0 is at 25 degrees Celsius, not at. The delta H is going to change based on temperature. So what should happen is, from what I can tell, if it's at 5, putting it into water at 25.
Wouldn't delta H have to be
So-
bigger to balance?
Wait a minute.
So you would have to have a larger delta H.
Wouldn't you do negative Q of the water equals negative Q of the...
Yeah, but see, it's still going to be the Q of the solution will be equal to the Q of the water.
Right, so
So-
now your temperature changes.
So what's going to happen, what should happen is you should get a higher temperature change.
Isn't
Starting at a
isn't
much
negative
lower
Q of the
temperature?
water?
One of them will be negative, I just didn't write it in, but one of the sides will have to be negative. You should get a larger temperature change since you're starting at a much, much lower temperature. So since you should get a larger temperature change, you should get a greater A delta H value. Because all you saw here is, because we were at 25, the difference was only 3.2. So the assumption is because they're starting so much further apart that this temperature change should be greater. And I'm just trying to see through an equation how to justify that. Because I know delta H should be greater because the temperature change should be greater.
What if you just plug numbers into the
Yeah, you'd plug numbers into the
equation?
Q
So,
and show
you'd
that
plug
it's-
numbers into the solution in H2O,
this,
just put X as your final temperature.
so this number should be, this number, we know this number should be the same, right? See, again, each of these, and here's the problem with this, is if you're trying to use this, these are all at 25 degrees.
So
All these
delta
numbers,
S
they all
is the same.
change, because they're all going to change at
Yeah.
that temperature. I don't think you can use any of these equations to justify. That's what I'm trying to see in my mind if you can. The only justification comes in the fact that because the two are so much further apart, you're going to have to get a much greater temperature change. So there has to be a much greater temperature change, so delta H has to be greater. But I thought there might be a way to show that with an equation, but I don't think there is.
So you're saying that the final
Well-
temperature of the reaction is still going to be 21.8 degrees Celsius?
I'm trying to. wondering
Well,
if-
couldn't
Will
you
that make it then an exothermic reaction?
See, but it can't be. It can't be that much.
Wait a minute, couldn't
Because
you
because if you're
find
adding it at
delta
zero,
T?
I mean, it's an endothermic process, no matter what way you do it.
Yeah. So will
But
it be
now, if it's an endothermic
less
process,
endothermic because it's colder already?
well, where does the water? The water itself is starting at 25. Is that right?
Right.
So the water itself is starting at 25. So the water is going to experience, as we saw here, the water is experiencing a negative temperature change. It's going to have to experience a much bigger temperature change if the urea is already at 5.
Right.
Yeah.
So that's where I would assume. That's the only thing that makes sense to me. Is, I mean, it would have to, because the cold urea would cause this huge temperature change. So not only, and I would assume that the problem comes in twofold here. Not only are you getting the temperature change just from the reaction, but you're getting the temperature change from the actual coldness and hotness. So that makes a lot more sense when you think of it that way, that you're getting at least when you added the urea, it was at room temperature. So the only temperature change you saw was from the reaction itself. Now you're actually seeing urea that has a colder temperature. So that makes more sense that you have to not only overcome that as well.
Okay.
So that makes sense. That must be where that comes from. That's the only I can, like in my mind, I was trying to think of a way to describe that other than temperature change has to be bigger, so delta H has to be bigger, but there's no other way to show that, I don't think. Just the fact that because you're starting with much colder urea, if it's an endothermic reaction, it has to go down even further than that. So.
Is that from the chart? Remember the chart we had that said like, if delta G is this, it's spontaneous at high temperatures only, low temperatures only.
But yeah, but this doesn't really give us,
That doesn't
this
really
isn't a
work.
reaction, it's a dissolving process.
Okay.
So I mean, I don't know that that fits in. Because this would be, I mean, delta S in this case is positive. Delta H is also positive. So if that's true, delta G will be negative whenever, and if you look at these, this is absorbing, gaining more entropy. This is like boiling.
Yeah.
So it's only negative at high temperatures.
Okay.
So I mean, I don't know if that really helps with this. Okay, that's the first two. Don't have really a lot of time to get into this next one. I guess we can pick it up here next time. But just to give you an idea, the next one is a redox reaction. And they tell you it's generated blah, blah, blah. You have 25 milliliters of 0.2 molar NaCl reacts completely with the excess KMnO4. CO2 produced is dried and stored in the sealed container at 20 degrees Celsius. The pressure of CO2 in the container is 0.5. So calculate the number of moles, calculate the volume in liters. Part A, I don't see as being much of a problem because it looks like it's just a matter of stoichiometry. Oh, so we have the molarity and the volume for part A. That's easy enough. The volume of Cl2, well, you have PV equals nRT that you could solve that.